Okay, in these examples, we're going to take a look at the sample mean as a variable, keeping in mind that if you collect one sample after the next, you should expect the value of the sample mean to vary from one sample to the next. So in that sense, it's a variable, and we're trying to answer some questions based on figuring out the distribution of that variable and maybe answering some probability questions. So example 1 says it's known that the mean IQ score on a certain test is 100 with standard deviation 15. Describe the sampling distribution of the sample mean IQ for samples of size 36. You got to keep this in mind when you're asked a sampling distribution problem. You really want to focus on three things. First, can you say the distribution is normal? Then, you can always apply the formulas to find the mean and the standard deviation. So is it normal? Then what's its mean? Then what's its standard deviation? So remember, there's two conditions that we can say the sample mean would be normal in distribution. If they tell us our population is normal, then it's a done deal. The sample mean is also normal. If they don't say that, then what we need is a sample of size 30 or more. So here we have a sample size of 36, so that means we're set. So I'm going to start my answer here by just saying the sample mean, or if you just want to use the notation x bar, right? But the sample mean is normal. Really, it's approximately normal because of the sample size of 30 or more, but we're just going to say it's normal. And then you can just write it out verbally, say mean equals, or I'll do both. I'll write it verbally, but put the symbol there. Remember, the symbol would be the mu for the population mean, and then as a subscript, the variable. So mu x bar means the population mean of the variable x bar. Our formula was that that mean is always equal to the population mean of the individual data values. So the mean of all the possible sample means is also equal to 100 because 100 was the mean of all the individual IQ scores. Finally, I got a comment on the standard deviation. The notation, if people are just more into giving the notation, sigma for the standard deviation for a population, it's of the variable x bar, so that is a subscript. That formula was always the population standard deviation of the individual values. So here it told us the standard deviations of individual IQ scores was 15 divided by the square root of the sample size, so divided by the square root of 36. Normally, I leave my standard deviations just like that. In most cases, there are clear units that we could also put on these values. So if the mean was something measured in hours, we could say 100 hours and the standard deviation of this number of hours. Here with IQ, if you were going to do a unit, you would do points as the unit. So, I mean, you could say 100 points and this many points, 15 over radical 36. Normally I leave it like this because it's difficult to simplify. Here, 36 is a perfect square, so radical 36 is just 6. So in this case, it's really 15 over 6. So I can simplify that. That would be 2.5. And that's it. I've commented on whether it's normal. I found the mean, and I found the standard deviation. So that is a complete answer for one of these sampling distributions of the sample mean problems. So this example wants us to do more. It says, based on this, find the probability that in a sample of 36 people who took the test, the mean IQ score is more than 95. Well, it's nice that sample size was 36 above and it's 36 here. That means I don't have to tweak the standard deviation at all. I already know what my distribution of the sample mean is. Since it's normal, we can apply the normal approach to answering questions about probability. So this is asking me what's the probability that a normal variable, here it happens to be x bar, but a normal variable is more than 95. So applying the process, we're going to sketch a normal curve. label the mean, which was 100. All right, we got 95. And we wanted the probability that a sample mean is more than 95. Here's the whole trick. Trick number one is you want to make sure you're using the normal approach to probability because your sample mean is normal. But then the part that people forget you've got to use the proper standard deviation when you're calculating the z-score. So remember, the next step would be calculate a z-score, which would be 95, the data value, minus 100, the mean. But I got to divide by my standard deviation of the sample mean. Because this was a probability question about the sample mean, it was not a probability question about an individual IQ. Had this been phrased, find the probability that a randomly selected person has an IQ above 95, then that would be a question about an individual data value, so you would use the standard deviation for the individual values, which would have been 15. Here, probability question about the sample mean, we got to use 2.5, the standard deviation of the sample mean. Well, that's convenient here because 95 minus 100 is negative 5. Negative 5 divided by 2.5 turns out to be negative 2. So negative 2 exactly is going to be negative 2.00 in our table. We're still using table 5 there to find our areas under the curve. And this is not very clear, but remember you're going to look up a z-score by going to the ones and the tenths digit. And then up here is the hundredths digit. So we want 2.50. Nope. Let me go back and check. What was our z-score? Our z-score was negative 2.00. Okay, so remembered the wrong. We want negative 2.00. All right, so negative 2.0. Hundredths place is also 0. So this value here is going to give me my area to the left. So it looks to me like that's 0.0228. But remember, the table area gives us the area to the left. So this was this small area over here to the left of 95. To find the area to the right, we're going to subtract that from 1. So now that's going to give me 0.9772 as my area to the right, and the answer to the question, the probability that our sample mean would be greater than 95. So again, if you're good at doing the normal probabilities, you're going to be good at this. This is the only trick. Remember to use the normal approach, and remember that we have to use the correct standard deviation. All right, let's see something else here. Example 2 says the wait times for callers to a customer service center have a mean of 7.4 minutes and a standard deviation of 2.7 minutes. Find the probability that in a sample of 50 randomly selected calls, the mean wait is under 7 minutes. Okay, so they don't ask us to do a sampling distribution of the sample mean here. Whether you write this out fully is kind of up to you, but the trick to answering a problem like A is to recognize that you have to make sure that your sample mean is normal in order to really answer this question. So if the sample size was 50, we know our sample mean is going to be normal. So I jot this down as notes in the beginning. Really, I'm basically setting up, here's my sampling distribution and my sample mean. X bar is normal because the sample size is 30 or more. The mean of my sample mean is going to be that population mean of 7.4 minutes. And the standard deviation of my sample mean is going to be the population standard deviation of 2.7 divided by the square root of the sample size, so divided by the square root of 50. And again, here there's a natural unit in minutes, so we'll put it in minutes. All that does for me is sort of organize my process, because now I kind of remind myself I'm dealing with a normal variable. Here's the mean, here's the standard deviation. So I've got a problem again. It's asking me, find the probability that your sample mean here is under 7. So the normal approach, we sketch our curve, label our mean, label the data value of interest. We're looking for an area to the left, right, because it says probability that your wait time is under 7 minutes. I'm ready to do the z-scores. The only part to really watch out for, can't divide by 2.7 here. That was the standard deviation for the individual wait times. We have to divide by the standard deviation of our sample mean. One of the reasons I like to leave my standard deviation like this is that if you convert that into a decimal, you're likely going to get slightly different answers to all of these questions than is in any textbook. Right? If you convert it to a decimal, you got to end up showing a bunch of decimal places. So whatever this works out to, let's just say sigma x bar is 0.361847623, etc., etc. Write a bunch of those out if you want to write it as a decimal. I would rather see it as this ugly fraction than as a lengthy decimal, and I like to make sure that my values match the book. When I punch this up on the calculator, this is basically the sequence that you would want to do if you just want to enter everything all at once. Start with a parenthesis and do the numerator, 7 minus 7.4, and end your parenthesis. Then hit the division button, start a parenthesis for the denominator, 2.7 divided by. Now when you open up the square root, it opens up a new parenthesis. Type in 50. One parenthesis closes the square root. A second parenthesis closes the denominator. And if you punch that up all in one line, we should end up having to, as always, when I punch this up, I'm going to round it off to 2 decimal digits. But let's see, I'm getting z equals negative 1.05. So there's my z-score. Now this is convenient. Area to the left is exactly what's given in my table. So I know that my probability for this problem is going to be equal to whatever value I get from the table. Check, make sure I read this right. It's easy to be shifted 1 over, but I'm getting 0.1469. So that's the probability that the wait time for the sample 50 calls would be under 7 minutes. If we look at the next one, part B, same type of question, but the language used makes people think it's much harder. Because when people read this, they see the phrase sampling error. Right? So it says, determine the probability that in a randomly selected sample of 50 calls, the sampling error is at most 0.5 minutes. Sampling error just refers to how far your sample mean is from the population mean. So a different way to phrase this, would be find the probability that our sample mean is between, having the sampling error be at most 0.5 minutes means we're looking from 0.5 minutes below the population mean up to 0.5 minutes above the population mean. So here our population mean was 7.4 minutes, right? Given in the original problem, 7.4 minutes. So if we did 7.4 minus 0.5, that would be 6.9. So we're looking for the probability that X bar is between 6.9 and 7.9 minutes. So that's not a problem. Again, it's a normal variable. We're going to sketch our normal curve. Put our 7.4 in the middle. We're going from 6.9 up to 7.9. And the probability would be the area in the middle. One nice thing here is, since we went half a minute below the mean and half a minute above the mean, I only have to do one z-score calculation here. Whatever the z-score is for the positive one, for the 7.9 minutes, the other z-score is just going to be the negative version of it, since we're the same number of minutes to each side of the mean here. Alright, so again, we can punch this up on the calculator in one step if we kind of throw parentheses around everything. And I'm getting 1.31. That means this z-score is 1.31. This one's negative 1.31, if we look at the z-scores here. Alright, well, we don't end with the z-scores. We want to find the area in between. That gives us the probability. So remember the process. We're going to look up the z-score for 1.31 and get the area to the left from the table. And again, you always want to do these problems on your own. Check, make sure I don't read something wrong, because I do make careless errors just like you guys. If we look up positive 1.31, I'm getting 9,049, so 0.9049. Now we're going to subtract the area to the left of the smaller z-score. So when I look up negative 1.31, I'm getting 0.0951. 9 minus 1 would be 8. Here we'd have to borrow. 14 minus 5 would be 9. We'd have 9s there. We would have borrowed 1, so we'd have an 8 there. So it looks like 0.8098 is our probability. And that's it. We're really doing the normal probabilities again. We're paying attention to the scenarios of sample sizes of 30 or more, or if we know a population is normal to begin with, that's when we can say our sampling distribution is normal. We have the two formulas for the mean and the standard deviation, and then we can do all kinds of probability questions just like we did for regular old normal distributions. All right, so give the homework problems a try. Message me if you have any questions, and good luck, everybody.